So today we're going to talk about arithmetic sequences, or some people might say arithmetic sequences. Um, I tend to think of it, I don't know the exact correct pronunciation, like which one's all legitimate, but if you say arithmetic sequences, that's fine. To me, arithmetic sounds more like an adjective. I don't know, that's the way I heard it said when I was in college. So you'll probably hear me say arithmetic, but if you say arithmetic, that's totally fine. So we're learning about arithmetic sequences or arithmetic sequences. So an arithmetic sequence is an ordered list of numbers that has a common difference, right? The difference between each pair of consecutive terms is the same. So that means that it's a list of numbers that goes up by the same amount every time. A sequence is just a list of numbers. So to be a sequence can be any list. It doesn't have to be like a common difference. The common difference going up by the same amount each time, that's what makes it arithmetic or arithmetic, right? Adding the same number every time to get to the next term. So a sequence, anytime we're talking about a sequence, we can use this notation. And we call that the nth term. So the first position, the first term, that is A1, meaning that the first term in this arithmetic sequence. The second one is A2, A3, A4, A5, and then the generic term or the general term, we call it A sub n, which is just the nth term. Some books or authors, you'll see instead of using the A, they'll use like a T for saying like term number 1, term number 2, term number 3. So you might see those used interchangeably. Okay, so that's the little notation that we use. A sub n is the nth term of the sequence. So A sub 1 is the first term, A sub 2 is the second term, and so on. So in an arithmetic sequence, the difference between each pair of consecutive terms is the same, and we call it the common difference. And we use the variable d for that. So the common difference is d, and you can look at the sequence to figure out what the common difference is. Here, the common difference is 5. It goes up by 5 every time. Okay, so here's a quick example. Write the next 3 terms of the arithmetic sequence. Well, let's analyze this term, this sequence. To go from A sub 1, the first term, to A sub 2, what happens? We go, how much does it go up or down by? It goes down by 7. It's like we're subtracting 7, right? -7 minus 7 is -14. Then if we subtract 7 again, -14 minus 7 is -21. -21 minus 7 is -28. So all we need to do to write the next 3 terms of the sequence is from -28, we're going to subtract 7. So that would be -35. And then we are going to subtract 7 again. So -35 minus 7 would give us negative 42. And negative 42 minus 7 would give us negative 49. So the next three terms of the sequence would be negative 35, negative 42, negative 49. Now there's also the idea of being able to graph a sequence. So to graph a sequence, we are going to say that the term's position number n is the x value, and the term a sub n is the y value. Okay, so so when we plot an ordered pair, it's going to go like this: n, meaning the term number, and then a sub n is the actual term. So if these down here are a sub n's, these is a1, a2, a3, a4. Then the a's or the n's would be this is 1, 2, 3, 4. So if we're making ordered pairs in the format n comma a sub n, for the first term, n is 1, and then the a sub n is 4. For the second term, n is 2, and a sub n is 8. For the third term, n is 3, and a sub n is 12. And for the fourth term, n is 4, and a sub n is 16. So we have 4 ordered pairs that we can plot on the graph. There's 1, 4, 2, 8, 3, 12, 4, 16. And then what do you notice? What do you notice about these dots? What do you notice about the graph here? So this is the graph. But what you should notice about the graph is that the points are all lined up. The graph isn't necessarily a line because the domain is discrete. We don't have like a 1.5 term, right? We don't have a term that's halfway in between. So there's not a point right here. But the points that we do have are in a line. So in a sense, this is kind of a linear function because it has a constant rate of change. Whenever x goes up by 1, y goes up by 4. X goes up by 1, y goes up by 4. Oh dear, why is that thing still there? Okay, now, example 3. We're trying to identify an arithmetic sequence from a graph. Does the graph represent an arithmetic sequence? Well, let's see. Let's think about this. When x goes up by 1, so from 1 to 2, what happens to the y value? It goes down by 3. So when x went up 1, y went down by 3. So then here, x goes up by 1 to go to 2, from 2 to 3. What does the y do? It goes down by 3. And again here, x from 3 to 4, x goes up by 1. What happens to the y value? It goes down by 3. So does this one have a constant difference? Since it has the same difference each time, that's a common difference. What? This pen is silly sometimes. We have a common difference of -3. So yes, this graph does represent. Because we have a common difference each time, it does represent an arithmetic sequence. Because the x value goes up by 1 each time, so that can be considered the first term, second term, third term, fourth term. And you have a common difference. So if we were to write the arithmetic sequence, it would be 15, 12, 9, 6, ... Okay, now, since we just realized that arithmetic sequences basically are linear functions, it would be good for us to figure out how to write these sequences as functions. So, because the consecutive terms have a common difference, the entire sequence has a constant rate of change, right? Constant rate of change was how we described a linear function. That's the slope, the constant rate of change. The rise that happens every time you run a certain amount, right? That's your slope. So, which is the change in y for every certain change in x. So the points represented by this sequence lie on a line, and you can use the first term and the common difference to write a linear function that describes the sequence. So for this sequence that we're going to look at right now, we're going to let the first term be 4, and the common difference is 3. So here are the numbers, right? The first term is 4. The common difference is 3. So our sequence goes like this: 4, 7, 10, 13. This is the sequence that we're working with. It goes like this: 4, 7, 10, 13, ... So what we want to say is, can we come up with a formula for that, where we can say, all right, well, way down the road, what's the 25th term going to be? So let's take a look at it. In the first position, we have the first term, right? Just a sub 1, which is 4. For the second term, a sub 2, we have the first term plus one of the common differences, right? So in this case, it would be the first term 4 plus one common difference, which is 3. 4 plus 3 is 7. To get the third term, instead of saying like, oh, it's this term plus 3, you can say, well, adding another 3 is just adding another d, right? So the third term is the first term plus 2 common differences, right? So you'd be adding 3 twice to get 10. Then the fourth term is the first term plus 3 differences. And so the pattern that you start to see is that to find any term, the nth term, it's just the first term plus n minus 1 differences. Remember when we found the fourth term, it was 3 common differences. And when we found the third term, it was 2 common differences. When we found the second term, it was only one common difference because the first term is just the first term without a common difference. So say you wanted to find the 100th term, you would do the first term plus 100 minus 1, which is 99 differences. So hopefully that makes sense. You can kind of see how that pattern works out there. Whatever term you're looking at, you do the first term plus one less than that differences, right? The common difference times one less than the number of the term you're looking for. All right, let's look at that. This is the equation for an arithmetic sequence. So here's what it means. To find the nth term of any sequence, all you do is you take the first term and then you add a certain number of common differences. How many of them? One less than the term you're looking for, right? So this little n number here will be the number of the term you're looking for. So if you're looking for the 100th term, then 100 minus 1 would be 99, and you do 99 times the difference. So that's the formula. Now we're going to use that formula. So example 4 is to write an equation for the nth term of the arithmetic sequence and then find the 50th term. All right, so we just learned that the formula for the nth term of an arithmetic sequence is a sub n, the nth term, is the first term plus n minus 1 times the common difference. Okay, well, I need to figure out what I need to fill in a number for A1 because I can know what the first term is, and for D. And then the n, I'm going to plug a 50 in to find the 50th term. So the first part is to find the equation. So I need to know, so right here, the first term is 14. So I know A1 is 14. And then I need to figure out the common difference. Is my common difference going to be positive or negative? Well, my numbers keep going down. So that means that my common difference should be negative. So what's happening each time? How much is going down by? 14 down to 11, that's minus 3. 11 minus 3 is 8. 8 minus 3 is 5. So my common difference is negative 3. Okay, so let's find the formula. So our formula is like this. A sub n equals A1, the first term. So my first term is 14. Plus n minus 1 times my common difference is negative 3. Now, this is technically an equation for the nth term. Later on, we'll go through the distributive property and simplifying it to get it to be in the form of y equals mx plus b. But for now, all we need to do is we have an equation for this that'll generate the sequence, and we just need to find out the 50th term. So to find a 50, we just take our equation and we plug in a 50 for n. So 50 minus 1 is 49. So we're doing 49 times negative 3. Hey, buddy. That wasn't my calculator button. So 49 times 3 is 147. So 49 times negative 3 would be negative 147. So we're doing 14 minus 147. Minus 147, negative 133. So could you have just kept going minus 3, minus 3, minus 3, minus 3 50 times? Yeah, you could have done that. But algebra makes it so that we can analyze the process, come up with a formula, and then now we have a shortcut for finding. You wouldn't want to do this if you had to find out the 200th term. You wouldn't want to do that 200 times. You'd just do 14 plus 199 times negative 3. Okay. So we just started using this formula, and we can put it in function notation by replacing the a sub n with f of n. So a function where n is the input. And then so the last time we did a sub 50. So the notation for this one would be we would be doing f of 50 instead. But on the right side of the equal sign, the exact same thing would happen. We would still plug a 50 in for n on both of them, end up doing 49 times negative 3, right? So it's the same, it's just this is in function notation now. And now, considering it a function, the domain is the set of positive integers. Because if you think about it, for an arithmetic sequence, the only values that n can have are term numbers, the first term, second term, third term. So only whole numbers, right? So the set of positive integers. So remember, the domain is just positive integers. So remember that part about the domain being only positive integers? When we graph the function, we have to remember that it has a discrete domain. Which means like it can only be 1, 2, 3, 4. We can't have 1.5 or 1.6 or anything like that. So that means that we only have graph on the whole numbers, 1, 2, 3, 4. We're not going to have any graph in between them. So our graph is just going to be dots. Okay, now, example 5. Online bidding for a purse increases by $5 for each bid after the initial $60 bid. So the first bid was 60, so 60 is A1, right? A2 is 65, A3 is 70. But what's the common difference? D equals 5 because we're adding 5 each time. So to write a function, we would say, all right, f of n instead of a sub n equals a1 plus n minus 1 times d. We know what a1 and d are. A1 is 60 plus n minus 1 times d is 5. But so this is a function, though. We want to kind of try to simplify the function. So we're going to distribute the 5 through. So we get 5n minus 5. And then we can combine like terms with the 60 and the negative 5. So this is going to be 5n plus 60 minus 5 is 55. So here we have like the simplified function, right? All we did was plug in for A1 and D and then distribute and combine like terms. So here's our function, f of n equals 5n plus 55. Graph the function. Well, in order to graph the function, we can only graph it where the domain is defined, right? So we don't have there's no zero, because when zero happens, there's no bids. We only start it when there's one bid, right? So one bid puts us at $60, right? So the term one, the value was 60. So 1, 60. 2, 65. 3, 70. And 4, 75. So that's the graph. You can see that it's growing at a linear pace, but you also need to keep in mind that there's no graphing between the dots because we don't have 1.1 bids or 1.5 bids. So this is the whole graph. Well, at least for this part of the domain, it goes on forever, right? You'll have another one there, and then it keeps going up and over. So that's part B. So here we got the answer to part A is over here. The answer to part B is here. So for part C, the winning bid is 105. How many bids were there? So for the winning bid to be 105, that's $105, and we need to find out what was N, right? So what we're going to do is we're going to plug 105 in for the f of n, and then figure out what n had to be. So if the output of the function was 105, then that 105 has to equal 5n plus 55, right? If we take the function f of n equals 5n plus 55, we're substituting 105 in for the outcome of the function. And then we want to find out what n would give us that. So all we have to do now is solve for n. So we subtract 55 from both sides. Get 50 equals 5n. Divide both sides by 5. We get n equals 10. So that means there were 10 bids. All right, so we learned about what an arithmetic or arithmetic function is. It has to have a common difference. So it's going up by the same amount every time or down by the same amount every time. Then we learned that we could write functions. We could write functions with them, that they always line up linear. And we could find the function for a sequence and then use that function to predict the outcome later on. All right, so that was a fun lesson. I will now stop the recording.